Hey, so it's time to figure out what is the theory that helped propel continental drift to being widespread accepted. And one of the big contributions of that was another American geologist named Harry Hess. And Harry Hess was not only a geologist, but he was also a naval officer during World War II. And one of his big contributions is that we were looking to find places to land our boats in a safe way. And so they started to use this sonar technology to sort of map parts of the ocean floor where they would be landing their boats to make sure that they could actually land there, that it wasn't too deep down, that the boats would get through. So they developed the sonar technology, and the way sonar works is you send out a signal, and then if it bounces back really quickly, it means it's closer to you. If it takes longer to bounce back, it's further away. And basically, by mapping out these sounds, you could sort of map out where your area is. So when they were starting to do this in World War II, one of their big discoveries was that on the ocean floor, it wasn't totally flat. There were sometimes like underwater mountains, sometimes called seamounts, and sometimes there were jagged edges, sometimes it was further down. And this was a big discovery. It was just something that people didn't really understand about the ocean floor. So Harry Hess would go on to basically popularize this new theory that was called seafloor spreading. And without his contributions earlier on, he wouldn't have understand how this mechanism works. So again, you send the sonar down, and then it will come back up, and then we get a rough map of what the ocean floor looks like. So Harry Hess came up with this idea of seafloor spreading, which occurs at the mid-ocean ridge, which is the longest mountain chain on Earth. Most people, when they think of the longest mountain ranges, they might think of the Rocky Mountains or the Andes. But truthfully, it's underwater. It starts over here in Iceland and it goes all the way down through the middle of the Atlantic Ocean. The mid ocean ridge actually stretches all around the world. But the most famous area in which it happens is in literally the middle of the Atlantic Ocean. So that's why it's often referred to as the Mid Atlantic Ridge. But we can use the Mid Ocean Ridge. Mid Atlantic is just a more specific region that they refer to there. So it's located underwater on the oceanic crust right here. And another person that really deserves a lot of credit here is Marie Tharpe. Marie Tharpe worked underneath a person named Bruce Heezen. Both of them worked at the Lamont Doherty Earth Observatory, which had a different name at the time, which is actually only located in Palisades, New York, about 15 minutes away from Old Japan, which is pretty cool. And while she was there, she noticed that there was all of this seismic activity, essentially earthquakes that were happening, minor earthquakes that were happening on the floor. And she basically took all these data points that she collected and she mapped them out. She plotted them on the data chart. And she realized that they happened right along here, which perfectly matched up with the mid-ocean ridge, the underwater mountain chain over there, and basically helped prove that this was volcanically active. And if it was volcanically active, that means there was magma that was coming up at the center over here, and it was kind of pushing away this tectonic plate over here away from this tectonic plate over here. And the dangerous part about doing that was she was essentially helping to prove Alfred Wegener's theory. Alfred Wegener, known as a laughing stock, her boss Bruce Heezen was like, "Don't do that. That's you don't want to end up like Alfred Wegener," and dismissed her discoveries as just girl talk, which was kind of famous last words because although Bruce Heezen made a lot of important discoveries as well, he's kind of forgotten in history. And Marie Tharpe, was really the one that is now remembered. She should be remembered even more, but she's kind of a local legend around us, which I think is just so cool how she made her mark on geological history like that, propelling forward this theory and helping people know that continental drift did happen. And the way that it happened is this. So seafloor spreading happens at the mid-ocean ridge. So as this plate over here, this tectonic plate is moving to the right, and this tectonic plate is moving to the left over here, that leaves a little gap. And because of that, the magma that's sitting down underneath, that's part of the asthenosphere, well, there's now an opening, and that hot rock rises up. It comes up here, it comes into contact with that freezing cold water that's at the bottom of the ocean, and it very quickly just cools and hardens into brand new crust. And as this happens over time, right, the older crust gets pushed further and further away this way and further away this way. You can actually date the ages of the crust and reverse time and realize that as this happens, the continents slowly move away from each other. So it's this heat that is escaping out that's causing it to rise up, that's pushing. Imagine two different conveyor belts. If you ever been to a grocery store like ShopRite, you put your groceries on there and then it slides over to the area where you're going to check it out. So imagine you have one going this way and one going this way, and gradually over time you can rewind the clock and know that they started at the same place, but they wind up in different places over there. And this is how we can realize that this happens. Now, the force underneath that's causing this to happen is a force called convection. So convection is because as it, it's hotter at the bottom of the mantle than it is at the top. Why? It's closer to the core, and it's much hotter in the core than it is at the top. So because of that, it causes the hot rock to rise up to the top. And when it gets to the top, it's colder up here, so it has nowhere to go. It winds up moving off to the side, cooling down and sinking because denser things sink. So hot rises, cool sinks, hot rises, cool sinks, and that happens over and over again. And this motion of convection is dragging these two plates apart from each other, which is what is allowing seafloor spreading to take place. The problem with this is that if you continue to do this, you're going to create new crust in one area. But you can't just create new crust forever. If you do that, planet Earth will grow, it'll get bigger. And that's not what really happens to planet Earth. Instead, it kind of recycles everything in a process called subduction. So subduction is when a tectonic plate crashes into another tectonic plate over here, and it winds up going back down into the mantle where it melts back into the liquid magma that becomes back into the mesosphere over here. So it essentially gets recycled as it falls down. This happens in an area called deep ocean trenches. If a mountain is sticking out, like it's land that's sticking up, this is like land that's sticking down right over there. So that's subduction. So here's another GIF that kind of shows you what's going on over here, this conveyor belt. So here, oceanic crust is, by the way, the only thing that does subduct. It crashes into the continental crust over here. And as it's moving down, whatever was at the top over there, like the top layer of it, winds up melting and it winds up fueling these volcanoes over here. So it's actually kind of like a transfer of oceanic crust to continental crust. This new oceanic crust gets created over here. But also gases that were stored in the form of rock over here get released as gases that then get returned to the atmosphere, such as carbon dioxide. So you can see over here, the Rift Valley. It's kind of an interesting thing because although they're moving away from each other, and you think it would be really like lower down, it actually winds up raising the rock in that area. So although they're moving away from each other, it winds up causing mountains to form in that area because the heat from the magma over there causes the rock to expand and can take up bigger. And that's why there's this underwater mountain range over here. And even though as you go further to the right over here, it winds up becoming more flat and more flat. But then over here, we have some underwater mountains called seamounts. So this video, I think, does a phenomenal job at showing what's taking place over here, right? We talked about that convection, right, as the liquid hot magma rises up to the top and then pushes off to the side, dragging the plates across, where eventually it winds up subducting back down into the mantle. And you can see that subduction taking place over there. So I just thought this was a very effective way to show all this taking place as the magma pools underneath here and then rises up through these volcanic eruptions over there back into the atmosphere.